So I'm gonna go over the config changes. So the difference with this, so we did a position controller on the azimuth like assembly the other day and used motion magic, right? So all the same garbage. The difference with this scenario is that we have like a static load due to the force of gravity. So when we get to our destination position, we don't want the motor to turn off because the error is so small, because then you'll end up with something like this. I haven't done this before, so we'll see if this messes everything up. Enable and go up. Oh, it just works. Wow. Oh, but okay. Anyways, without motion magic, I think what would normally happen is your error reduces sufficiently. You turn off your controller, the weight drops. You develop a bunch of error. You go back up, so you just end up oscillating about the set point. Anyway, so playing around with using the arbitrary feed forward term. So basically the output of your controller will always be some negligible value, right? So that value you would pick to overcome the external force. So it's like how much voltage is required to counteract the force of gravity. So that was like empirically derived. All right, what else? So in the configuration options, one thing that was like super important and easy to overlook, I think, was the neutral deadband. So basically, like, I think by default this is 0.04, so they're saying plus or minus 0.4% of your full range of output will result in 0 voltage out. So if you tried to command 0.035, you'll end up commanding 0. Negative 0.02, 0, right? So you coerce all your outputs. It's very similar to what we do with joysticks. So there's like a 0 output around center. That doesn't work so good for when you're trying to counteract like really small error. So you end up oscillating around your target position. I'll try to demonstrate this. Control enable, and we'll go up a little bit. Yeah, so you can see in the plot that there's like this oscillation in position, and the commanded output is toggling between 0 and 0.04. The 0.04 is like the threshold where we are allowing the motor to turn on. So we're in this error band where we can output nothing because of our deadband, or output something due to this parameter. So I'm going to save much smaller deadband, so like basically 0, 0.1% deadband. And so now any value that the controller derives that due to the error should result in an output of 0.01% of the bus voltage or greater, will actually result in the thing trying to command the motor. So if we enable, you can see to hold this position with the weight off the ground, it's requiring 0.03, somewhere around there, 0.02, 0.03 percent out. So with the default 0.04, the static output wasn't, static voltage output wasn't sufficient, right? So it was like turning on and off and oscillating. All right, so that is the neutral deadband. And then the rest of it is very similar to what we already did. So you have a P term. I enabled the I term to overcome some what's it called?
Steady state?
Yeah, steady state error. I'm not sure that we actually need that now that the rest of the system is set up right. And then I set a peak output because I just wanted to limit speeds in case like I did something wrong. And what else? The acceleration and cruise velocity. Right, those are the parameters you need for the motion magic. Right, so that's just like adding a trapezoidal motion profile or whatever. Right, it was slow acceleration up to a top speed, and we set the top speed to be 5 revolutions per second, with an acceleration that was something else. I don't remember. It was kind of just like fudged into a speed that was reasonable. So with all that set, I'm pretty sure that's all the parameters that we twiddled. We can, command pretty aggressively to our destination positions, maintain a load, or counteracting gravity, yeah, it works. Yeah, so this weight, it's like between 2 and 5 pounds. It's chosen to mimic the weight of the lift. After the load, like of a 150-pound robot, goes and is distributed across 2 Falcon500s, and then goes through a gearbox, right? So like divide that down, and you end up with like about that much weight. So it's an effectively equivalent load on that motor. So a good like demonstrational prototype, if you will. I don't know. So yeah, we'll go over this again as a class. Make a yo-yo, and eventually write the code into the subsystem, like just distill this into robot code. But that's the idea.